Okay, hello, guys, can you hear me? Test, 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 one, two, three. Please send a chat message if you can hear me. That would have mean a lot to me. Shit, I did not post the goal in my super working here. Okay, so the goal was to continue with the GAN, but what we ended up doing was probably fixing my stream. You can hear me, okay, that's awesome. How will I get started? What hazards? Okay, fine, fine, fine. So, all right. So how is the quality? Okay, I got 0 viewers now. That's awesome. I compared to my own, I think the quality is significantly better, right? All right, please let me know if the quality is any better. Looks good, awesome. Thank you so much, Lumi, for pointing it out because I've been streaming for more than 12 hours with an extremely bad quality now. But people were watching me and they seem to be enjoying my content. So hopefully that is a good signal that they are willing to put up with my content even when I'm not doing anything. 1 second. What's it? Yeah, sure. Sta hier. No worry. Never mind. Ciao. All right. Sorry for that introduction. Intermission. Uh, okay, so um, where were we? So we fixed the stream now, and the stream looks good. The quality looks good now. Um, okay, so I'm gonna let's see how much time we have left. I mean, time left in the sense of our cycle. Oh, so we only spent 15 minutes on fixing this. So um, let me think about it. So I'm gonna change the text here, and then I'm gonna get back to actual machine learning because that is the goal of the stream, right? So select. No, we're gonna reset the transformation first. Gonna reset the transformation. Then we are going to we're gonna make it bigger. I'm gonna remove the screen for a second here. We're going to make it bigger. Properties, make it bigger. Like let's say 100. Is that good enough? 100. Okay. And then we're gonna put it in here. 100 is too big, it seems, so we are going to make it a tad smaller, and that looks fine now. Yeah, so we are all set to continue with our goal of understanding GANs, right? So where were we? So the goal was to understand with GANs. So what we did, we ended up doing fixing my stream. Thanks so much. Really appreciate it. Any distractions? Yeah, I mean good ones. I mean yes, good ones. We were reading the paper. So for those who just tuned in, how much of a summary do you guys want? So what we did is we read through the paper, we crossed out most of the stuff, and we're only staying with the relevant stuff. We made an image over here of what a GAN is, what a GAN does, and how we are going to train it. And if there's one person with GAN experience, I would love to hear him explain to me, because I honestly don't know this, what happens with the original labels of the data. Because I'm giving a quick summary again of what a GAN is or what a GAN does. So we have some random noise over here. We have some random noise over here. We're going to pass that in the generator, and the generator is going to create fake data. Think of it as money. We have a team of criminals, or counterfeiters, and they are generating fake money, fake currencies. Then we also have real currency, right? But the discriminator, the discriminative model D, it is his job to act like a police and to separate the fake from the real currency. By sequentially first training G and then D and then G and then D again, we can make both models better. So we increasingly we make we get more realistic fake currency, but at the same time, we make the police better at capturing the fake currencies, right? So Juan Carlos Paco is saying only gin experience, the drink. Wait a second, there's a big discussion about Haskell here. It's all represented as functions. Loops are done by function recursion. Wow, really? Loops are a function recursion. Yeah, I want to understand monads as well. It's just a monoid in the category of endofunctors. Those are two words I've never... I don't know. It's maybe it's a lot of terminology first. We are working on GANs here. Maybe we can do a tutorial on Haskell as well, if some people like that. Because I mean, Haskell isn't necessarily machine learning, but in my honest opinion, I think that machine learning is just hyped up statistics, like hyped up statistics, and just functional optimization, right? Because if you look at a neural network, I think we did that in the first stream. A neural network is just a series of functional transformation according to some parameters, and then we are looking for the parameters that optimize some certain loss function, right? So it's just beefed up statistics. So, I mean, and statistics, of course, is mathematics. So, yeah, so it's hipster statistics. Yes, it's indeed hipster statistics. Extremely hipster statistics. Nah, but you know, like, I think that artificial intelligence is a very interesting subject because, of course, you can make a lot of cool movies with it, like The Matrix and The Terminator and stuff. But it also gets a lot of media attention because saying that, like an artificial intelligence robot learned to predict stocks generates clicks and revenues, right? But if you say, well, our optimization routine in Python converge only weekly, then you're probably gonna get fired as an editor if you write that, right? But that's basically the same thing, in my opinion. So let's continue with GANs, because the goal here today is to finish our GAN. I said one stream ago or two streams ago that we want to you want to set small goals that you can achieve, such that you get motivated to achieve more goals. But figuring out a GAN is our top priority right now. So let's get back to the paper. We discussed all this, which was a very dense little piece of nugget with a lot of symbols. The symbols, we noted them here in my Emacs. Yes, I use both Vim and Emacs because I'm a heteric. I use org mode. I started with Vim 4 years ago. Then I dabbled in org mode like since last year. I dabbled in Emacs because of org mode. I think org mode is really cool. No. Good question. Spacemax, question mark, asks Juan Carlo. This is not Spacemax. This is regular Emacs using a Spacemax skin. Yes, that's right. So I started from Vim, and then I thought, okay, so as a Vimmer, well, how do you get into Emacs? And then I got into Emacs, but it has so much custom keybinds that I was not willing to invest the time in to really switch from Vim to Emacs. So what I ended up doing was I ended up using both Vim and learning Emacs vanilla on the side, just reskinning it as Spacemax, because I think this Spacemax looks absolutely gorgeous. I think this is like one of the most beautifully designed, I don't want to say IDEs, but I think Spacemax has just a beautiful visual design, and I just copied that because I thought it was awesome, right? I use all GUI on Emacs. Ooh, yeah, I disabled all GUIs. But I mean, whatever floats your boat, right? I'm not a. I actually made a good friend in the Holy War, where we So I saw this guy in class using Emacs, and I like whispered in his ear like Vim is better, and then we started talking, and we became very good friends. He's in Spain now, but and he works at I think the central bank. But that was that was very funny. Okay, so enough about Vim, enough about Spacemacs. We can talk about this at the end of the stream, I think. Oh no, Lumi says another Vim Emacs combo user here, but I also use IDEs with Vim plugins. Vim Emacs just can't compete when reading code. Yeah. Yeah, that's a good question. I think that, yeah, like, I think there are some plugins to make reading code easy, right? But indeed, like jumping through big code bases is something I think you have to invest a lot of time in. And I think indeed IDEs can be very helpful for that. So I see my Vim as a tool. I see Emacs as a tool to get like more work done, right? To write good software. I think that's our main goal. And whatever tool you use, if you use a pen and paper, right? All those plugins are not even close as good. Yeah, okay, I'm gonna be honest here. I have like very little actual industrial software engineering. So for example, I've never worked on like a code base with more than 100K lines, right? So I've never worked on like production scale stuff. So I can't really speak about my experience in like traversing big code bases. Um, but yeah, okay. I did have a timer running, right? Yes, my timer is running. 100K is already pretty big. Yeah, okay, but I mean, of course there are like gigascale, exascale, right? Okay, so we did this. I think we can strike it out, underline it. I want to underline it. Is there any way to underline this? No, whatever. Okay, in other words, D and G play the following two-player min-max game with value function V of G and D. So I'm gonna write this down and I'm gonna dissect it for you guys. I'm gonna make a screenshot over here. Gotta make a screenshot. Can I paste that immediately? Let's see if this works. No, I can't paste it. Can I open this in? I want this one. I want to open it in Photoshop. Open it in this one, right? Hello? Hello? Where's my image? Please, image. Okay. Let's do it like this. Okay. And let's get this in here. All right, awesome. So, let's see, what do we have here? So, in other words, I think we can remove this one. I think we can, or at least we can kind of drag this down a bit. In the next section, we present a theoretical analysis. Okay, this is not really, okay, so this is a smart object, which is extremely annoying. I'm gonna have to rasterize this layer first. Rasterize the layer, sure. Now we can finally edit the layer. There's not too much actually, so let me think about what is written down here. So we're gonna think about over what is written down here, and it's actually quite easy. Well, it's not easy, but it could be worse. What we have here is so what are the arguments that we are minimizing and maximizing over? So we are minimizing over G, and we are minimizing over D, and we are minimizing some value function D and G. So what parameters, so let's just disregard this thing for a sec. So let's just only focus on the first part. So what are the things that we can optimize over, right? What are the things that we could change here? Yeah, scrolling is extremely slow. I agree. So the only things that we can change here are the parameters. We can only change theta G and theta D. These are the weights of the artificial neural network here and the weights of the artificial neural network of the generator. So those are the only things we can, assuming that the prior is like a hyperparameter that we kind of specify beforehand, right? So those are the only things that we can change. So we are optimizing over theta G and theta D basically. Oh, by the way, if anything is unclear, please feel free to reach out in the chat. I'm happy to explain everything all over again. If you just want to say hi in the chat, please say hi in the chat. I like it a lot if people are active in the chat. If you want to think along with me, I'd really appreciate it as well. So yeah, just have fun. If you have any questions, do not hesitate. I'm more than willing to answer any questions you guys have. So so we are minimizing over G and D, but what we're actually doing is we are minimizing over theta G and minimizing over theta D, right? And then what are we minimizing exactly? We are minimizing the expected value, where I'm going to leave this out for 1 second. No, this should be a square bracket. We're going to minimize the expected value of the log of the output of the discriminative model, which of course is indexed by the theta D, plus, and I'm going to run out of space here, plus the expected value of the log of 1 minus the discriminative model of the G model of the parameter Z, where G is the generator. So G is indexed by theta G, and D, of course, is indexed by theta D. All right. Then I omitted these things, but this first thing, I'm going to do it in a different color. So the first thing here, let's make it purple. So we take the first expectation, we take it over the data. We take it over the x's, where the x's come from the data. So this is the expectation over the data. So over P data, where so this is so this is the discriminator, right? So this is the police guy, and the police guy tries to maximize his probability of assigning the correct label. So P data here, the x's mean all the x's. So it means both the fake data and the real data. So the data we're talking about here, so P data is like all the data. Then here we have the here we have the bad guy, or the generative model, and the generative model is, we take the expected value, we take it over the distribution of the prior data of the random noise, right? So Z was the random noise we put in, and we take this expected value over Z of Z, PZZ, where Z was the data. So this is the distribution of the data. This is the distribution of the noise that we put in the generator to generate the new samples. Okay. Is this clear to everyone? Or did you guys know this already beforehand? I'm really wondering if I'm able to kind of give you guys more understanding of what GANs are. I really hope I've been able to do that by dissecting the value function here, because it has become a lot more clear for me now. But I hope you guys feel the same here. Or if you guys haven't been paying attention, you can also say that, and I'm happy to repeat everything I just said, because that also kind of makes me learn it even more deeply, right? Or maybe you guys aren't even paying attention and I'm just talking to myself here, which is another third and very interesting option. Okay, so I'm gonna take a silence as that everyone understands it, or everyone just nods their head in silence. So, okay, we have the value function. That's the next sentence that we found. Okay, so we did this. Nice. Okay, in the next section, we present a theoretical analysis, creating training criterions, recover the data are given with enough capacity. Figure 1, a less formal, more pedal. Okay, so let's see figure 1. The generative adversarial networks are trained by simultaneous update B and D. Sure. In practice, we must implement the game using an iterative numerical approach. Optimizing D to completion in the inner loop is computationally inhibitive. Instead, we alternate between K steps. Hint, many people have streams running as background noise, listening to a podcast or something in tune when something interesting comes along. Yeah, I know that. Someone told me yesterday that he was listening to my stream while working on his 3D printer, so that was very cool. Yeah, he knows. Yeah, I'm kind of new to this stuff, so wait. So thank you guys so much for actually improving my stream by making me realize that I was streaming in really bad quality. I hope the quality is better now. I'm pretty sure it is, right? I'm pretty sure you guys can actually see something now. So, in practice, we must implement the game using an iterative numerical approach. Optimizing D to completion in the inner loop of the training is computationally prohibitive and would result in overfitting. Instead, we alternate between K steps of optimizing D and one step of optimizing G. This results in D being maintained near its optimal solution as long as G changes slowly enough. This strategy is analogous to the way that SML PCD, I don't know what those two things are. This is formally presented in algorithm 1, sure. So the main idea is that we're going to optimize. So this is the training idea here. So in practice, equation 1 may not prove sufficient gradient. When G is poor, D can reject samples with high confidence that are clearly different from training data. In this case, log 1 minus DGZ saturates, right? I think we talked about this where we said that if DGZ becomes 1, we get log 2 minus, we get log 0, which is minus infinity, which happens if the discriminator is able to, if the police works very well, then the generator won't have any any chance to improve its model because the police is so good it's able to pick up it's able to pick up every fake fake currency bill, right? So what we then do is, okay, I'm gonna write that down. So I'm gonna write it down. So it can happen that log DGZ log DGZ saturates as the police is too good, or the discriminative model, right? What we then do is, rather than training G to minimize log 1 minus DGZ, we can train G to maximize log DGZ. So what we are then to solve this, instead of minimizing, instead of training G to minimize the probability, the log probability. So instead of training G to minimize the log probability of getting caught, we maximize the probability of fooling the police. So what I'm saying here is that we already figured this out. So we looked at the edge case of the value function, and we noticed that because we take the logs, if dgz becomes 1, we get log 0, which results in minus infinity. And so rather than training G to minimize the probability of being caught, we can maximize the probability of fooling the model, which does not degenerate because, well, this can also degenerate, right? Because we still have a log, and if this becomes 0, it's 1. If it becomes so log 0 is minus infinity, log 1. Yes, so, okay, so instead of, yeah, so this doesn't degenerate. This objective function results in the same fixed points, but provides much stronger gradients early in learning. But if this is true, why don't we just always maximize the log GDZ here? Why don't we just always do that? I mean, isn't minimizing the chance of getting caught, which is this thing, isn't that exactly the same thing as maximizing the probability of fooling the algorithm, right? That's my intuition, at least. Or even, why can't you do both, right? Why can't you minimize the probability of getting caught and / or the probability of getting of this one? Interesting. Something to think about. Okay. So here's figure 1. Do we want to analyze this picture? It's supposed to be intuitive. Okay, so let's try. Figure 1. Generative adversarial networks are trained by simultaneously updating the discriminative distribution, D, so D is the blue line, so that it discriminates between samples from the data generating distribution, black, PX from those of the generative distribution, green. So the fake data is green, the real data is black, and the police model is blue. So I am going to make a picture of this. Okay, so let's say we have the real data, it's white, right? Let's say the real data is white. My Mac only has 2 USB slots, so okay, so we can get rid of this. So let's say that the real data is white, The real is white. The blue is the police model, the discriminative model, right? It's the discriminative model. And the red is the fake model. Or I think I made it green early on in the video. So let's make it green. Okay, so let's draw some real data first. Do we have a color picker here? Color picker. What's the shortcut? I think it's I, but I'm not sure. It's I indeed. Okay, that's my timer to take a break. But I wanna do figure 1 and then let's take a break, okay? So we can let that sink in. Figure 1. So if I recall the image here, we have some. I should make this better. Why is it not? Okay, so do it like this. Do it like this. And like this. All right. So let's draw some real data. The real data looked as follows. We had some data here, right? Just say it's a Gaussian distribution. We can do better than that. Then we had the generated data that looked something like this. And we had the discriminative model that looked something like this. Furthermore, we had some 2 lines here. One of them was Z, and the other was X, and we kind of had it like this. Okay. So let's see what they say about figure 1 here. So generative adversarial networks are simultaneously trained by updating D. So we're going to update the blue line, that's the police line or the discriminative model, which separates the fake data from the real data. We have the data generating distribution, that's black. So that is the actual real data or the distribution of the real data. And the lower horizontal line and the generative distribution PG. The lower horizontal line is the domain of which Z is sampled, in this case uniformly. So we sample Z uniformly. The horizontal line above that is part of the domain of X. The upwards arrows show how the mapping GZ imposes the non-uniform distribution PG on the transformed samples. Okay, so that's a lot of words in one sentence, but the key idea here is that we have a generator function, right? That generates fake data X, where we take Z to be uniform. So we just generate some random Z's. We have trained some function X, and that gives us some new fake examples, which we can try to fake the blue line with. That's the key idea here. Then G contracts in regions of high density and expands in regions of low density. I don't understand this. G contracts in regions of high density and expands in regions of low density. Okay, that makes sense. So, yeah. Consider an adversarial pair near convergence. So I think that's the C. PG is very similar to P data. So the green line is very similar to the dotted line. That's smart. They use data dots and green for G. And D is a particularly accurate classifier. So D is relatively good. So the police is relatively good. The inner loop of the algorithm D, so of the discriminative of the police model, is trained to discriminate samples from the data converging to D star. P data, it converges to this. Okay, interesting. C. Okay. So okay, so it just takes a weighted it just takes the probability of these two. This is actually way simpler than I thought. So it just takes the ratio. So okay, so I actually used this in my thesis. So I wrote a thesis about what is it? Financial econometrics. And I used exactly the same concept here. Um, but actually this is exactly the same the concept. So I could have used some cool buzzwords like adversarial, but I did not because I didn't know it was the same concept. So what they're doing here is actually very easy. So what they're saying here is that it converges to basically this. You take the ratio of this plus this and you divide it over the total ratio. That's it. So after an update to G, so after updating the generative model, the gradient of D has guided the generative model to float to regions that are more likely to be classified as data. After several steps of training, if G and D have enough capacity, they'll reach a point at which they both cannot improve because they overlap, right? So if we can perfectly fit the distribution of the training data, then the discriminative model will not be able to separate them any longer. All right. So that's the intuition behind training a GAN. And again, just like yesterday, it turns out that training a GAN is actually significantly, it takes way more time than expected to get all the ideas really down in and nitty gritty. I thought it would be a simple 1-day experiment, but it might even turn out to be a 2-day or a 3-day experience here. So the timer went off. So what did we do this stream? Let's note down the ending time. It's 13:16. We fixed my stream. We chatted about functional programming and Haskell. Lumi1337 helped me with stream bitrate. I interrupted the stream a bit and got back online. Then we read through the value function of the GAN and how to train it, gaining a better and deeper understanding of the concepts behind training a GAN. All right. So that's it for this cycle. I'm going to take a quick break, make some tea. Hopefully you guys are willing to stick with me. Don't go anywhere. I'll be back in roughly 5 minutes. If you have any questions, you can of course always contact me via chat or DM or whatever. If you like my content and you want to see more of me, don't hesitate to follow me. I would greatly appreciate it. And yeah, so I hope you guys are willing to stick with me for the coming 5 minutes while I take a break. In the next session, I think we can finally wrap up. I think I have a good idea of I'm going to skip the theoretical results and I'm going to get straight, maybe I'm going to do the algorithm here, then I'm going to get straight to the straight to seeing what kind of amount of layers he uses in especially the prior that he uses, right? So we need to get the prior with using cross-validation. So there are a few hyperparameters that we need to choose, and I think choosing them is quite important. So stay tuned. In the next session, we're going to select the hyperparameters and try to finish reading the original paper. I'm going to take a quick break now for 5 minutes, and I hope I will see you guys soon. Okay, guys, I'm back, or at least sort of back. Oh yeah, I'm back now. Um, if anyone's listening, I was wondering, you guys can hear the fans pretty loud, right? Or is it fine? Because I just checked out my stream downstairs on a different computer, and the fans were really loud. But maybe it's. I hope it's not too noticeable. I hope it's not too noticeable. White noise is fine. Okay, is it? Okay. So I have these quiet comfort headphones, and I was wondering maybe I could use these. Maybe I could use this microphone, whether that was a good idea or not. I'll probably try it out on a test stream. Not now, but maybe another time. So yeah, I'm gonna take a sip of water, which I forgot downstairs. Okay, that's fine. I still have some tea and this beautiful mug from SpaceX, a company which I fully support in all their endeavors. I hope the drinking noises aren't too loud. Okay, so let's set a timer and get back to work again. Set timer for 45 minutes.
For how long?
45 minutes.
Your timer is set for 45 minutes.
There we are. All right. Yeah. So, what is the... Okay, let's go to the super work schedule. What is the one thing that I want to accomplish this cycle? Let's see. Let's have a look at the paper and see how much we can do, actually. Because the paper is 9 pages, but we are at page 3 already. This is theoretical results. The global optimality is not that important, I guess. And then we want to look at the experiments, right? So basically, we only have to do 3 papers. So I want to make the goal today, or not today, but in these 45 minutes, to finish reading the paper and make the final decisions about, like, to finalize and crystallize the views of how to train, how to train the GAN. I think that should be possible. So we want to finalize the ideas of training the GAN, EA, finish the paper. We could start programming. Oh my god, oh no, I forgot it again. Oh my god, wow. Okay, yes. I forgot it again. Oh no. Thank you so much, Danis, 1994. Where are you from? I haven't seen you around. I think this is your first message, right? I'm happy to have you here, man. If you just tuned in, we are working on GANs right now. So we are working our way through the original paper of Ian Goodfellow. I think he's either at Google or Facebook now. Pretty big guy. He invented GANs. And the key idea here is to have two AI models. It doesn't necessarily have to be neural networks, but to have 2 models and make them fight against each other. That's the key idea here. I hit the notification. You guys can see everything now. And we were in the process of filling in this. How will I get started? Well, just continue. What hazards? Internet, phone, social media, Twitch chat, maybe? But usually those distractions are good because they provide valuable constructive criticism. Yeah, so let's continue where we left off, right? Yeah. So, theoretical results. Okay, I'm just gonna strike through everything that is unnecessary, and I'm going to plug in my mouse again. I should really buy a USB hub, but first things first. So, the generator G implicitly defines a probability distribution PG as the distribution of the samples GZ obtained when P comes from the distribution of PZ. So, wait a second. So, the generator G implicitly defines the distribution as the distribution of samples when G is Z. So we generate noise, then we transform the noise into data, into fake data, which we have here. So let's go up. So what he's saying is we generate noise, we put it in the transformator, in the generator, we generate fake data. This fake data has a certain distribution. So it implicitly, okay. Therefore, we would like algorithm 1 to converge to a good estimator of P data given enough, okay. The result of the section done in the non-parametric setting, infinite capacity, sure. We do not, okay, we can strike out most of this. It's non-parametric, infinite capacity, sure. We will show that it's a min-max game, global optimum. Okay, we're not that interested in theoretical results right now. Oops, whatever. Okay, minibatch. So we do a minibatch stochastic gradient descent of generative adversarial networks. The number of steps to apply to the discriminator k is a hyperparameter. K is 1. So for k steps, wait a second. Okay. The number of steps to apply to the discriminator k. Let's try to get before we delve into specific. Let's see if we can understand the algorithm in its generality. So we start. So we have a number of training iterations. Okay. So for, let's say, 1 iteration or 2 iterations, we take k steps where we can choose k ourselves. So this is k is 1, for example. So we can just forget about k right now. We sample mini batches of m noise samples. So we sample m noise. We sample mini batch m examples from the real data. We sample m mini batches from the data generating distribution. Okay, we sample noise. We sample mini batches. Then we update the discriminator by ascending its stochastic gradient. Sample mini batch of m noise samples. Update the generator. The gradient based updates. Okay, I don't understand this. I do not understand this at all. Okay. Okay. Wait a second. Okay. So, step 1, we do this a lot. Like we do this a number of times. Step 2, we do the mini-batch thing k times, where we can choose k ourselves. So let's say k is 1. Step 1, we sample a mini-batch of m noise samples from the noise prior. Okay, I'm gonna draw this because I don't understand it. I mean, I understand it. I understand that step, but I don't understand the following step. So let's get a nice color in here. Which color haven't we used yet? Purple. We used purple. Red, blue, blue. I don't think we have used blue yet, right? So let's use blue here. So this image is starting to become a bit crowded. So in the very first step, we sample m mini batches of noise samples. So we sample m. So step 1, we sample m here. We sample Z1 to Zm. That's step 1. Because what I'm confused that he doesn't say, okay, and then we transform this into. Okay, so what I would expect him to say now is to say we transform this into fake data, but the fake data is implied by the functional transformation here. If you can, so we feed forward the noise and we turn it into fake data, but that is not like, it's not mentioned explicitly. So my expectation after reading this sentence was, we generate the data and we transform the data into, we transform the noise into fake data using the generator that we have right now. But that is done implicitly here. So this could definitely benefit from the Python cone. Explicit is better than implicit. But then again, it's an academic research paper, right? So okay, so we understand this sentence. We can highlight that. That's awesome. So then we sample a mini batch of m examples x1 through xm from the data generating distribution. So what I think it is that we just take a random sample from this distribution here. So x1 through xm. That is that step. That's reasonable. We can highlight this because we did this. So the P data here is not the fake data. It does not include the fake data because the fake data is just the noise, right? Then we update the discriminator by ascending its stochastic gradient descent. So we update the discriminator. We update the discriminator. We update the discriminator. Let me think about what that means. We update the discriminator. Sorry for repeating a single sentence so often, but so this was step 1. I mean, or step 0, depending on your preference. This was step 2. Then we update the discriminator, step 3. So we update theta d plus equals, and then the gradient, right? So in step 1, we sample new data. No, in step 1 we sample new noise. Then in step 2 we sample real data. And then in step 3 we let the discriminator, we train the discriminator using the generated noise and the generated data. Okay. Very clear. Using this loss function, right? So we take the expected value of this, which is exactly equal to this, right? It's exactly equal to this. The only difference is that, so we take like the expected value, but we drew the x's from the data. We generated the z's from the noise prior, so we can just take this in one big 1 over m summation thingy. Ooh, yeah, yes. So we understand this. Wait a second. Do I truly understand this? Do I truly understand this? Because we need the gradient of this. So what is our loss function? What is the loss function that we are using? Okay, I don't actually, like, I understand what is being said here. I understand what is being said here, but I wouldn't be able to code this in at the moment. So I have one clip. Someone clipped something, so that's very interesting. Very curious to see what someone clipped actually. Okay. Okay, let's abstract away from this and imagine we understand, and then we come back to it, and hopefully we get a better understanding of the whole picture. Then we can fill in the blanks of this and how to program it in. So step 3 is still a bit vague. So we're going to say that step 3 is still a bit wonky, right? Step 3 is it has a bit of spikes we have to be careful for. Then we sample minibatch. So that is updating the discriminator. Then we sample new noise. Okay, we take another sample of M from noise. So that's step 4. We sample new Zs. And so we understand that. That is fine. And, oh, wrong one. And then we update the Ithul says, this is the best approach to AI ML. To be honest, so many people just try to implement without understanding. Yeah, that is. Yeah, thank you for kind of giving some feedback on that, because I think you need to be honest about like what you understand, what you don't understand. Ideally, in the business world, I'd love to be able to do that as well. Like say, okay, I have no idea what's going to happen, but there you have sometimes to convince people, and you cannot always convince people with the truth, right? You can convince machines with the truth and facts, but a lot of people are, I mean, people kind of by definition, I don't want to say by definition, but people are not rational in the sense that we're not emotionless, cold-blooded Terminator machines that calculate our expected utility, right? We calculate some form of expected utility with a lot of heuristics, a lot of biases. So Ayethel says, there's too many people running around saying they're data scientists just because they know how to use TensorFlow. I hope I don't become one of those. So I'm trying to indeed, I don't know if I can call myself a data scientist. I'd like to. I do call myself a data scientist, but that's kind of because everyone else is calling themselves a data scientist. So, I mean, you have to market yourself in some way, and I hope I have the credentials. And here, we're trying to learn together, and hopefully, hopefully I won't let down that label of data scientist, right? So, like it's kind of a philosophical question. At what point can you call yourself an engineer, or at what point can you call yourself an artist? I think it's important. It's a fun exercise to think about, but I wouldn't spend too much time on it personally. I think. Ayuthel says, my future is in bioinformatics, but I'm still in an undergrad though. Yeah, I think bioinformatics is so cool. I think honestly, like wetware and hardware and software, like I think that the brain is just so cool. I don't know how to say it differently. I think it's just, I mean, I've talked about this a lot in my streams, or not a lot, but like a disproportionate amount of time. Then I would never start talking about this to random people I know, because they don't care, right? But maybe you guys care. I mean, you're watching me stream artificial intelligence and machine learning, so I hope you guys are interested in stuff like the matrix, right? Like, how can you prove if someone is in a simulation or not? I mean, we are writing simulations here. Like, if imagine you're inside one of these simulations, can you figure out, like, how could you figure that out? Or I think that the brain is also a very interesting thing, right? Because we take in a lot of sensory input. In reality, the world is way richer than we can see. There are like alpha rays, gamma rays, beta rays. There's sound. There's infrared. There are different spectrums of color we can't see, right? So the world is way richer than we observe, and we only observe a very small and noisy subset of the world. I mean, you know that we can only see this much sharp, right? The rest of our vision is blurry, and so our brain takes in all that input from our sensory organs, and then it does something. It does something. We don't know what, but it does something. Like a biological machine does something, and then it outputs something, right? And I think that is very interesting to think about. So Ayethel says, I'm a biochem molecular biology major transferring to bioinformatics major next year. Genetic sequences fascinate me, and genomic data science. Yeah, that's also cool, man. I think there are like, with these kind of things, you always run into some trouble with regards to, I don't want to say ethics, but like, if you had a disease that would kill you in 5 years, would you want to know? Like those moral questions, and especially like, not even would you want to know? Of course you want to know, but if you get it tested and your insurance provider would also know this, like, would you want to do that? And I think there's a very big moral hazard here. So I studied applied math, and I also had a course in insurance, right? And a very important thing in insurance is the concept of moral hazard. Someone that is more insured, someone that is insured might take more risky decisions because he is insured exactly for that reason. So that commands higher premiums. Louis says, to be fair, a big part of being able to use those things productively means you need to develop intuition, and you can only get better at that by experimenting with it, playing with it. Also, the theory doesn't usually talk much about engineering limitations. Yeah, that's very true. That's yeah, you're making a very good point here. I think indeed, if you really kind of like want to know something, if you claim you know something, you need to know it inside out, and you kind of need to chunk it. I don't know if you know about the concept of chunking, but you need to like have done something so often that you can do it while sleeping, that you can do it from the back of your hand, right? Like handwriting is something that each of us has grokked. Maybe grokking is the better word here, right? So to be able to grok something is like putting on a sweater or riding a bicycle. Riding a bicycle is like it's like 1,000 mini actions, right? Keeping your balance, pedaling, looking around, avoiding obstacles. Like biking is a seriously difficult operation, and we humans do it like daily here. All right, I missed some in the chat. Well, in the USA, it's illegal for people to get tested for HTG, Huntington's disease, without the parents' consent. It's dominantly inherited, so if the children have it, the parents have too. If the children finds out, they know the information about the parents. What? It's state specific. I live in Australia, so I don't know the legislation. Wait, what? So it's illegal for people to get tested for Huntington's disease without their parents' consent. What? So if the children have it, the parents will too. Or at least one of them, right? If the child finds out they have it, they know information about the parents. Wow, that is crazy. But so imagine it like, so that's so weird. So if someone gets tested, if a kid gets tested without the consent of his parents, and then the insurance provider finds out that the test results are positive, would that mean that it's like fruit of the forbidden tree, that evidence would be deemed void because it was obtained under illegal manners? I think so, right? I think that an insurance provider is not allowed to use that information in court or to like change the premiums. That's actually crazy. That's crazy to think about, right? Yeah, those mental diseases, like, there's also this concept of like the ship of Theseus, right? Ship of, I think it's called ship of Theseus. Like, or the axe of Lincoln, of the U.S. president. Like what do you have to, like, how much of an object do you have to change such that it's not the object anymore? So whether a ship that has all its components replaced, does it stay the same thing? So why I came up with this, or why I bring this up, is because, like, if you miss a finger, or if you miss an arm, right, you miss a leg, you can still, with reasonable accuracy, say, okay, this person is the same person. But like, how far can you go until that person is not that person anymore? And I think it starts with the brain. I think if someone has like a neurodegenerative disease, I think it's not the same person anymore. At least, of course, my view is open to being changed, but that is my current point of view on this issue. All right, so Aito was saying there was an infamous case as well where one identical twin wanted to get a genetic test, but the other one didn't. There was a huge legal fight because one twin would know the genetic conditions of the other. Wow, that's crazy, man. Always wanted to know, can you just not get your full DNA on a USB stick and analyze yourself? I have no idea. You should ask Aethuol, and because I don't know anything about genetics. It's very interesting to me, but I don't know anything about it. Thank you so much, guys, for hanging out with me. By the way, I really enjoy your company over here. Where were we? Wasn't 23andMe like hit with a data leak or something? Okay. We had step 1. We made new noise. Step 2. We sampled from the data generating distribution. Then we update the discriminator, which I did not understand completely, but we will get back into. We did that k times, but for now we say k is 1, right? Strike through. Then we sample new noise, and we update the generator by descending its gradient descent. So we update the generator by descending its gradient descent. So we are okay, yeah. So the last thing here is that in step 5, I think it's step 5, right? So 1, 2, 3, 4, 5. In step 5, what we're gonna do is we're going to this image is going to be so convoluted now. In step 5, we are just going to continue with this flow. We're going to take the Z here, and we're going to let it flow through here. And we are going to try and update the parameters here, such that we maximize the probability of fooling the discriminator. So ideally, we want to update the weights such that the discriminator gives 1 everywhere, right? Because we know we're putting in fake data. So that is how we update the generator. So the second step is updating the generator. Okay. So there's a big discussion going on in the chat about genetics. Huh. I remember seeing some graph of like the cost of genome sequencing and going down like rapidly, right? Cost of genome. I think there was like a huge exponential drop in the cost of exponential in sequencing, right? Oh, cost per genome. What is this? Moore's law. Moore's law is for. Wow, that's crazy. This is exponential scale, right? Yeah, my computer was a bit slow. This is exponential scale. That's crazy. In 15 years, or 14 years. Wow. That is falling fast. Almost 1K for cost per genome. Okay, so we because our goal right now, let's not get sidetracked. Let's see how much time we have left. We have 17 minutes left. Finalize. So our goal right now is to finalize the ideas of trading the GAN, right? So we wanna finalize the ideas of trading the GAN. So there was one piece missing that I did not understand completely yet, and that was how we update this. I think so. The variable we changed. So we changed theta d. That's the only thing we can change. I think we can just train the model. I mean, we can just update the weights, update the model here. But the problem I'm having in my mind is that I have the data, right? So you generate new data, you have the features. The features are just the pixels. You have the x's. But at the same time, the labels, you know whether something came from the real distribution or the fake distribution. And then we have to okay, I think I get it. I think because I'm kind of confusing myself because this is a number. So we output the probability of realness. That is what we output here. That's what comes out of this function here. And using that, we calculate the loss function, and based on that, we can optimize the model. I think I got it. So I confused myself by. So the key here is that the D function spits out a number. So D spits out a number between 0 and 1. And that is how we are going to optimize the model. We're going to optimize the model because D spits out a number between 0 and 1. And that's going to give some number. These are numbers, this is a number, log is a number, sum is a linear operator. These are all just numbers. And of course we can have a certain learning parameter, but I'm not sure if I am going to add the learning parameter. I certainly hope that the GAN will converge, because of course there is no guarantee that the GAN will converge anyway. So we might just set it to running like 10,000 iterations or 5,000. So I have spent a lot of time not coding actually, which is kind of bothers me here, but I guess it's needed because you don't want to start coding if you don't understand what you're doing. At least that's kind of my view. So okay, we understand algorithm 1 now. So if anyone has any questions about algorithm 1, anything that is not clear, anything that's not clear about algorithm 1, yeah, let me know. Yeah. I don't know what momentum is, but I think it has something to do with if a gradient is large, then in the next iteration you also overshoot it, or maybe some exponential decay in the amount of move that you in the size of the step. I think, but I have no idea to be honest. So I have to look that up later. So what is momentum? What is a gradient based? I think I have questions data. Okay, so we figured this out, right? So we did this. Look what OR can do. Wait, how can I? Shit. Oh, it should be in the list, of course. Let me see. Awesome, right? You can like have like you can tag it. I think this is so cool. And then you can even have this. What is it again? I think it's this. Awesome, right? Okay, so we need to learn what momentum is. Momentum gradient based learning. This is like the only reason I'm dabbling with org, because I thought this was so cool. Like this was like the only reason I'm using org right now is because I really like the check marks and the boxes. But it has some cool things. Okay, so this is like global optimality. I don't think we are that interested in here, right? So sup, yeah, sure, concluding the proof, fine. We're not interested in proofs right now. For G fixed, so we are extremely disinterested in this proof. So if G is fixed, we know the optimal discriminator. So why can't we just use that actually? But okay. 1 second, someone's calling me. Yeah? Yeah, mate? What's up? Ja, lekker. Thanks. Nu? Okay, 1 second. Okay, give me 1 second. I'll be back in a jiff, eh? Not in 5 minutes, like, I don't know, 2 or 3 minutes. Or 20 seconds. I'm back. I'm so sorry for bailing on you for 10 seconds. I hope you guys are still here. So let's continue. Here's a note that the training objective for this can be interpreted as maximizing the log likelihood for estimating the conditional probability. We can reformulate this. Yeah, I already thought so. But this is the optimal one, right? No, so say G is fixed. Sure. And at that point, it's used to minus log 4. That's an interesting number, minus log 4. So, minus log 4. Why minus log 4? So are these the same then? If everything is the same, then you get a half here, and you get a half here. So if they all are the same, right? Oh man, this is like straightforward math, but for some reason I can't think out loud. So you have like log a half plus log a half. That is minus log 4, yeah. My computer is really slow, sorry. Everyone sees why this is minus log 4, right? This is nothing new. I won't eat during the stream. You guys can probably hear it. Yeah, so this proof is probably trivial, right? Yeah, proof is a half, log half, plus half is minus 4. Best possible value. So we cannot do better than that, actually. By subtracting the expression from CG, VGGD, we obtain this, where KL is the Kullback-Leibler divergence. We recognize in the previous expression the Jensen-Shannon divergence between the model's distribution and the data generating process. All right. Since the Jensen-Shannon divergence between two distributions is always non-negative and 0 only when they are equal, we have shown that C star is the global minimum and the only solution is PDG. Okay. I could think about this deeply, but this is not the focus right now. What is interesting is that I actually contributed to the Kullback-Leibler divergence on Wikipedia. So if you go to the Wikipedia page, this is just a simple. This is just kind of a humble brag here. If you go to the exponential distribution and then you look at the Kullback-Leibler divergence, I actually wrote that. So if you see me bragging now and you think it's incorrect, feel free to change it because that's how Wikipedia. So I actually wrote this. If we click here, I actually wrote this. Cool, eh? I don't know. I think it's very nice that you can contribute to like Wikipedia and you can contribute to the human knowledge base. So yeah. I was at that time I was following like a PhD course in math, in asymptotic statistics, and we had to derive the Kullback-Leibler divergence for all sorts of different distributions, and I noticed that it was missing for the exponential one. So I thought, hey, why not just add it? So I made an account, I changed it on Wikipedia, and then no one changed it back. I think I got one typo or something. Someone typoed it maybe, fix a typo in there. But yeah, so I think that's honestly very cool. That's the wrong one. So okay, we actually don't care at all about this. Well, we kind of do. If we achieve something better than minus log 4, we know that we messed up somewhere, right? Because we cannot do better than minus log 4. So it does give us some bound of what we can expect to reasonably get, right? So these are kind of trivial. I don't want to say it's not trivial at all, but it's not that important for us right now. we're almost through the paper. I always claim that I don't like reading from the screen, but reading it line by line and having to recite it to you guys, actually, I think it's fine. Because it forces you to focus. So, convergence. Okay, I'm going to read this through this convergence part. I'm not sure if it's that. So, if they have enough capacity, the discriminator is allowed to reach the optimum as to improve the criterion. Okay. Then, okay. Consider blah blah blah, convex subderivatives, blah blah blah, blah blah blah, blah blah blah. I'm not gonna spend time thinking about this. I'm just gonna assume it's correct. In practice, adversarial nets represent a limited family, and we via the function. So in practice, adversarial nets represent a limited family of PG distributions. That makes sense, right? Because we only have neural networks. We only can approximate the distribution of the training data using a limited, like a finite set of neural networks. Well, technically it's countable infinite, I think, because I mean you can have infinite amount of layers, but for all practical purposes, I think we only have a finite amount of layers here. Let's say like 4 or 5 or 6. So we are kind of. Lumi is saying, I actually prefer NLab for math-related stuff. What is NLab? I've never heard of NLab. I'm curious. Could you tell me more about NLab? Sorry for eating. So I was saying, in practice, adversarial nets represent a limited family of PG distributions, right? So imagine that the distribution of the training set is like so we are approximating the distribution of the training data, and we only have so much neural networks we can choose from, which means that we have only so much weights to optimize. We only have so much weights and biases to optimize, which is given in theta g. But of course, this is our it's our parametric estimate of PG, right? So we're approximating PG using the neural network. Then the next sentence, I should probably read first the paragraph and then start talking. Using a multilayer perceptron to G introduces multiple critical points. However, the excellent performance of multilayered perceptrons in practice suggests that they are a reasonable model to use despite their lack of theoretical guarantees. So this is kind of pushing your luck here, right? I don't want to be mean, but it turned out that while this paper, I don't want to preface this with while. So this paper was huge. This paper was like so important, and GANs have become like the concept of the GAN that was introduced in this paper was a very important idea, like a very important thought idea. Like I don't want to say general relativity big, but it was important. And it turned out that GANs work, but they need a lot of fiddling. They need a lot of tuning, fine tuning, choosing the correct hyperparameters, using the correct. You have to specify a model for G, you have to specify a model for D, right? So in the first session, which you guys probably didn't join in on, which was at like 10 in the morning, I tried to get a high-level overview of how to train the GAN. I was unable to do this because I watched this video of this Siraj guy who does like also machine learning, but his GAN was so big. His GAN was so, he had like convolutional neural networks, and his first GAN was a convolutional one, like the G model, and then the discriminative model was like a deconvolutional one. So for me, that was a very convoluted expression. So the paper here just uses 2 neural networks, and the claim that he makes here is that it works. It suggests that it's a reasonable model, which is, I have to give it to him, that is very true. but it needs a lot of fiddling. So about NLab. I actually prefer NLab for math, but it's just another wiki for math, philosophy, and physics. Philosophy as well. That's crazy. It's deeper but less wide with respect to topics. Okay, our timer went off, but I want to finish. I want to continue working until we crystallize and finalize the ideas, so we can get back to coding, right? So we only have to do the experiments, and that's it, I think. So we only have to do the experiments. So that's the final piece we're going to do, and then we're going to take a quick break again. So we trained after, okay, we trained it. We can strike this through, sure, I don't care. CFAR 10, okay, we use a mix of ReLUs, not leaky, but regular. So the generator, okay, so okay, this is important. This is important. So this is not important, but this is very important. So the generator uses, come on, can I select something? So the generator uses a mixture of ReLUs and sigmoids, while the discriminator net used a max out activations. Dropout was applied in training the discriminator net. Okay, so this is key. This is very important. I'm going to write this down. Oh, that's the wrong one. I'm going to write this down because this is extremely important. Highlight text. So this is the information we're looking for, right? This is the money shot here. Let's see. So the generator model uses a mixture of ReLU and sigmoid, and discriminator model, discriminative, whatever, used a max out activation. I have no idea what max out is, but we can figure that out, I guess. Probably not too difficult. I think that like ReLU and sigmoid and probably max out, they're all, I don't want to say buzzwords, but they are just like jargon, right? So it seems intimidating. Oh, I'm using 20 pooled layers of mixed leaky ReLU layers, but it's just kind of words that people use to communicate it's just terms. It's not really, I mean, once you start using them, you realize that they're just functions, right? They're just functions, just like weirdly named functions. Max out. What is max out kind of like? So what would my intuition be if we see the name max out? What kind of activation can we expect? I'm thinking of a limit of like a parameterized logistic, right? So where we have like a binary. If it's larger than 0, what I'm seeing in front of me now is like kind of a saw shape. But let's just Google it because we could think about it all day. But let's figure out what a maxed out activation is. So max out activation. Maxed out activation is, what is max out in a neural network? Let's see. Shit, I should have kept like what I've learned. So what I've learned. What have I learned? Max out. I'm gonna learn that technically. All the, like how to train the generative model, how to train the discriminative model. We learned about the min-max game they are playing. I mean, then we mean the value function, right? We look at the optimal achievable loss, or the optimal achievable optimal achievable value loss, which was minus log 4. What else did we do? All right, so let's check out what max out is here. Can anyone explain what max out units are? Max out, also by Goodfellow. Wow. A max out layer is simply a layer where the activation function is the max of the input. Okay. As stated in the paper, even a simple MLP with 2 max out units can approximate any function. That is crazy. They give a couple of reasons to why max out may be performing well, but the main reason they give is dropout can be thought of as a model averaging in which a random subnetwork is trained every iteration and the weights are averaged. Since one cannot average the weights explicitly, an approximation is used. The approximation is exact for a linear network. In maxout, they do not drop the inputs to the maxout layer. Thus, the identity of the input outputting the max value remains unchanged. Thus, the dropout happens only in the linear part, but can still approximate. Okay, so I read this, but I did not understand the last paragraph here, mostly because I was just reading it and not really thinking about it deeply. So the goal here is not to necessarily understand why maxout is working, which is an idea for later, but right now what we want to know is what is maxout. And maxout is simply a layer where the activation function is the max of the input. So that's it, nothing more. And it is interesting that even MLP with 2 max out units can approximate any function. That is crazy. I think I have the paper on the, what's it called? Not the superposition, but like there's this, people think that neural networks and MLPs are working so well because neural networks have been shown to they're able to approximate any nonlinear function to arbitrary precision. I think it's called the universal approximation theory, neural networks approximation. My computer is having a bit of trouble here. Neural networks approximation theorem. Universal approximation theorem. Okay, there's no video about from 3 blue 1 brown here. That's a shame. I always loved that guy. Yes. We were almost done reading the experiment. Oh man, I'm getting tired. Like my brain is starting to feel no, I don't want to say foggy, but I'm starting to realize that I've been thinking a lot today. Uh-oh. What have I done? I was just trying to save the file. Anyway. While our model permits the use of dropout, we use noise as the input to only the bottommost layer. Okay, so we don't add additional noise. We estimate the probability of the test data under PG fitting a Gaussian Parsen window. Okay, I need to know what a Parsen window is. What is a Parsen window? So max out is just max of the inputs. What is a Parsen? Gaussian Parsen window. Like I know what a Gaussian distribution is. The sigma parameter was cross validation. This procedure was introduced by Brule et al. Exact likelihood results are reported here. The Parsen window-based log likelihood estimates. Sure. Figures 2 and 3 show samples from the generator after training. We make no claim that they are set better, but we believe these samples are at least competitive. Okay, that's awesome. The rightmost, nearest training, blah 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 blah, are fair random draws, not cherry-picked, unlike most other, show actual samples, blah blah blah, moreover uncorrelated, blah blah blah, blah blah blah. Okay, here. Fully connected model. Convolutional. Okay. So, while very interesting, was anyone able to figure out like how much layers they used, how many hidden layers, how many nodes, how many, like they say they are using multi-layer perceptrons, but how much, like How much parameters are there? How much... Is this an old paper or something? Like, I think maybe I have an old version here. Because I'm still left with like a lot of questions. Like, how much hidden layers? I think I can do Alt-Enter, Alt-Shift-Enter. How much how much nodes per hidden layer? Dropout. Like, I kind of know what dropout is, but I haven't programmed it in yet. Okay. So I'm scared I have I'm scared I have an old version here. Okay, this time I did not forget the BRB screen. Any distractions? Yes, 2, but it's okay. Did we complete our goal? Well, kinda. Like, kinda, I guess. So we finalized all the calculations and derivations of the GAN. The paper I have with me right now is extremely light on details on the amount of layers, etc., and the amount of hidden nodes, which I wish I could have gotten an indication of. Luby says the parsen window is just another name for kernel density estimation. Okay, it's about calculation of better distributions for continuous functions given discrete sampling. Okay, I know what kernel density estimation is. Why do they always need to make it so difficult with different names? Parsen window classifier estimation, right? Why is it always that they need to make it more difficult? Can you explain parsen window? It has better theoretical parsen Rosenblatt. About better distributions of continuous functions given discrete sampling, right? Kernel density estimation. Okay, I know what kernel density estimation is. I know that. But where's the parsen then? Oh, it's also termed the Parsen-Rosenblatt window method. Okay, so it's just kernel density estimation. Hey, just me, brah. Come on, brah. You tuned in late again. Or wait, you're from the USA, right? Wait, so what time is it there now? You just woke up then. Or were you from Germany? I forgot. Could you remind me where you're from? Hello. So this is Gaussian kernel density estimation. Not at all. Not at all what? You're not from the US? I'm from Romania. Oh, cool, man. Then we're in the same time zone. So yeah, you missed. Maybe I should make a schedule when I come online so you guys know. The quality should be way better now because someone helped me with the quality. I'm gonna set down here 226. No, 1426. 1426. Oh no, I did it in the wrong one. 1426. All right. You were in class. Yeah, sorry, man. Yeah, I'm streaming during a bit weird hours, right? So maybe I should move my stream to the evening so more people can get out from work, out from class. It's like GMT +1. Yeah, Amsterdam is GMT +1. So I'm just gonna take a break now. You just tune in at the right moment because actually what we did before here is not that interesting because I mean, it is very interesting, but you went over how to train the GAN, and so after this we're gonna try and program in the GAN actually using our homemade neural network, which is extremely basic. So that is what we're gonna do in the next session. Right now I'm gonna take a break again and have some food. I'm gonna take a break, and I will see you guys in like 5 to 10 minutes. I hope you guys are willing to stay with me here. All right. See you soon, guys. Yeah, you can always post things in the chat, of course. I'll be happy to answer when I see them. But I have to go downstairs for 1 second. Okay, I'm back, guys. Alright, I'm almost back now. I still have like 1 or 2 minutes I can take as a break. Whew. So how are you guys doing in the chat? Are you guys at work, or are you guys at like you finished school? Curious to see where my viewers are from. Romania, right? Alright. So, I'm here again, and I am going to get rid of the BRB sign. And then I have to admit that I am feeling a bit tired, so I'm not sure whether I'm gonna do 5 or 6 sessions, because I feel like my coding, I feel like I might not be able to write the clearest code in my current state of, because I did so much thinking already about trying to get my head around what a GAN is and how to train it, that hopefully I can still write some bomb-ass code. So, let's see. Oh yeah, so the problem we ran into is that the paper was extremely light on details, remember? So the paper basically... Oh wait, no. Let's start here. Let's figure out what is the one thing that we want to do in this cycle. Okay, so we need to train both the generator and we need to train the discriminative model. If we look at the algorithm in algorithm 1, then we see that we first train the discriminator. So let's start by training the discriminator, I guess, right? So, okay. Train the discriminator. If we're done, we can train the generator, but I don't think we'll get to there. How will I get started? Well, Python, I guess. Hazards, internet, Twitch chat, tiredness, I guess. Yeah, so this is gonna... So, okay, first... Oh, that's my break counter. Okay, I'm gonna set a timer again for 45 minutes. And we can get started. So, the exact definition of max out. So, the key thing that we are trying to understand here is to look at like what other okay, 1 second. New activation function called max out, which is okay, so this is the max out paper. I'm gonna copy this real quick. I'm gonna save it real quick. Project 002 GAN. Let's call this drop max out, right? This is the original max out paper. The original max out paper, so what does it do? It proposes a new activation function called max out. We have proven the universal approximation theorem. Okay. Max out propagates variations. Sure. Okay, do we have any definition of max out? Okay, the max out model is simply a feed-forward architecture that uses new type, the max out unit. Given an input, the max out simply takes the maximum. Wow, okay. So we literally just take the maximum of the z's, where the z's are, what are the z's? K, affine maps, pools, spatial locations. Yeah, it's like finding the max of the input, right? A single max out unit can be interpreted as making piecewise linear approximation to an arbitrary convex function. Rectifier linear. I think we should be able to program that in. But then if you can use max out, you can also use min out, right? Or min max, or like, why is it the maximum? Why can't you do the minimum? I mean, if you do the max, no wait, the maximum and the minimum have distinct probabilities, so that have distinct differences, but Stone Weierstrass. I was hoping I would never see the name Weierstrass again, but I'm afraid it follows me everywhere. Oh, that's a funny. This kind of looks like an exponential distribution or something, right? Okay, so in this session we want to train the discriminator. Okay, but okay, I'm gonna make some notes here. So, the original paper. So, we want to find out. Like what the original GAN paper is doing, right? How many layers? Like, maybe Google like original GAN paper architecture. Because the original paper is so light on details, there's basically no information what kind of architecture they're using. So this is cited by 5,000 people, so that seems like it's published. It's published in the NIPS. They maybe cleaned up the text a bit, added some nice graphs. Back propagation. Okay. Kigma. Kigma sounds very Dutch, by the way. Okay, so we read this together, right? We read this together, and we explained it together. So you have the generator that is minimizing over its parameters over theta g. Then we have the discriminator maximizing over theta d. We draw samples from the real data. Here we draw samples from the noise distribution, and we maximize the probability of accurately classifying, and here we minimize the probability of being caught, right? Then we update, proof, fine, and now this is what we're interested in. Okay, we use dropout, use noise only in the beginning. Again, where there is no mention of the parameters used. So we estimate the probability of the test set data under PG by fitting a Gaussian window, samples of G. Come on. I'm really stumped here. Has anyone read the original paper of the GANs? Because I cannot find anywhere classic SpongeBob Square. Okay, I'm gonna check this out. Give me a second. Medium GAN classic SpongeBob. Like I understand the concept and I understand how to train it, but all I'm interested in is trying to figure out like what the architecture is. I swear, this probably has like 20,000 claps. I'm pretty sure this is gonna be extremely popular. This post, if it allows it to load though. This is a big. All right, let's be patient here. Maybe it has to train the web page first before it allows me to see anything. I personally love SpongeBob though. SpongeBob is so nice. 6 minute read. Okay, so okay, 1.2K. That's decent. This morning I saw a post which basically explained nothing and was full with like machine learning buzzwords and had like 20K claps. Not even sure if that's anything meaningful, but it was extremely popular. So okay, so we have a GANs. Okay, so a GAN is a class of neural networks. Okay, I think the concept is a bit broader than that, but put most allow net to generate data in the same internal structure. Okay, I'm gonna be really precise here and say that this is false actually. So I'm gonna be kind of contrarian here because what I think is that it's not learning to generate the data with the same internal structure. No, it's approximating the distribution of the training data, and I think those two are distinctly two different things. But that's just my view, and I'm just trying to be kind of mean here, right? I'm trying to be critical. So if that description is too general, GANs are powerful and flexible. To make things more concrete, one of the more common applications is image generation. Okay. Say you have a bunch of images like pictures of cats. A GAN can learn to generate pictures of cats like those real ones used for training, but not actually replicate any one of the individual images. Is this true? I think it should be able to generate it, right? So given like if we have like an infinitely large generator model, which theoretically can perfectly capture the training distribution, then given infinite computational time and infinite random samples, we should be able to invert the generator to like we should be able to get one of the same images. If we look at the original paper, right? If we look at the original paper in Figure 1, so if we are in this case, if we are in case D, and the red picture, the black dots is like a cat, and then the green dot is our generator model. We should be able to like generate a perfect cat, but that would be classic overfitting. But okay, I digress. It's probably a very good tutorial. So if given enough cat pictures, it learns about the catness from the samples, the catness, and learns to generate image meet the standard. Furthermore, it does so without the generator having direct access to any of the training images. Is this true? Is this true? Yes, this is true. Well, kind of indirectly, right? Because we're trying to fool the discriminator, and the discriminator does have access to the training images. But so you can view it in two ways. So you can say, no, it does not have direct access. So, I mean, indeed, it says the word direct here, but it has indirect access, right? So GAN have, oh wow, I got a new follower. Thank you so much, Breakout11 or Break0 UT11. Thank you so much for the follow. I appreciate it. I'm actually gonna see if my follower goal updates. That is so awesome. Thank you so much. Yeah, so we're actually quite long already into the stream. We already did like 1, 2, 3, 4, 5. We're on our fifth cycle or session for the day, so we're almost done here. At least my brain is almost done. Let's keep it at that. So right now I'm critically evaluating a tutorial here, and why I'm being so picky is because if you try to like debunk every sentence you read, you start to critically think about like what is true and what is not true, right? I think this one guy got a Nobel Prize for trying to disprove Einstein's theory about light, and then he was unable to disprove it, kind of proving that light was both a particle and a wave. Maybe I'm confusing two things, but I recall something similar like that. So I'm trying to be critical here so that we can get a real clear-cut understanding of what a GAN actually does, and not what the media kind of hypes it up to be, right? Because that is what I'm most like that is what I'm most concerned with or most interested in. So we're talking about the access to the training images. So GANs have indirect access to the training images through the discriminator, right? GANs have been applied to more than images, okay? They can be used to generate short videos and robot behavior. That is a seriously cool application. That is really cool. In this tutorial, I'm going to walk you through behind the theory, unconventional way, using an episode of SpongeBob SquarePants. So it has a very high viral kind of... stick with me, the metaphor works much better than what you would think. I was thinking of using like a Westworld analogy, right? I don't know if you guys have seen Westworld. And I was thinking of naming the discriminative model Dolores, because maybe I'll make a YouTube video about that, right? Because, okay, she's a bit creepy, but Dolores is like, if you've seen Westworld, Dolores is like a, what's it called? Like an AI robot in like this kind of very luxury playground, and then she would be the police. But okay, so let's stick with me. We're gonna use GAN for image generation. So no weenies allowed. No weenies allowed. I remember this episode. I'm sad you guys don't have sound, but there's no sound actually. The salty spittoon. So where are we? A GAN works through the interplay of two separate networks, a generator and a discriminator. The goal of the discriminator is to tell the difference between the data generated by the generator and the real-world data we are trying to model. We can think of the discriminator as being the bouncer at a club. I don't just have any bouncer in mind though. The discriminator networks are like the bouncer outside of the salty spittoon. This is a nice... I kind of like the analogy already because it sticks with you, right? So in the world of SpongeBob SquarePants, you must be tough to get into the salty spittoon. The job of the bouncer is to tell the difference between the real tough guys and the weenies, the generated data. We have SpongeBob SquarePants, who is the generator. He's certainly not a tough guy, he's an imitator. And he needs to learn like a tough guy to get into his friend. Okay, so the analogy kind of breaks down here because the generator is actually a device that turns noise into a fake SpongeBob. So I think a generator would be like maybe SpongeBob's makeup. Maybe he'll get into that later on. Or like a disguise, you know? I think it should be more like a disguise. Okay, let me see. So no weenies allowed, blah blah blah. Through training, it learns to tell the difference between the real and the generated data. The first feature might look very obvious. Then the bouncer outside looks for a show of brute strength. Any real data should be able to pass this test, okay? Once the discriminator has learned something about what to use to tell the two apart, the generator can take advantage of what the discriminator has learned in order to learn itself. SpongeBob can use the fact that the bouncer is checking for strength in order to appear more like an actual tough guy. at the beginning, however, it might not be too convincing. Okay. Sure. Okay. The process doesn't end. It can be done millions of times. So kind of SpongeBob is like in this loop of like the SpongeBob's kind of in the loop of trying to get into this salty spittoon. Then fighting. Then SpongeBob picks a fight with someone. It's a nice analogy. I think it works. Okay. I think I'm being called. I have to take this. 1 second. Do I have to take this? No, I don't have to take this. So, putting aside the question, he has learned to imitate true guys, and he got in right. So with enough training, hopefully our generator can do the same. We can generate data samples that are not only indistinguishable from real data, but also to us as humans. Okay, so here's some math. If you have any questions about GANs, if you just recently tuned in and you kind of don't have the idea what we're doing, feel free to like post a message in the chat. I'm happy to explain. I'm happy to help you guys understand better what a GAN is, because that is the goal of the stream, right? This goal of the stream is to understand the GANs. It has taken us already quite some time actually to get like a general idea, but I think we're starting to get there slowly. To actually implement one, we need to get a little bit more formal. So we have two generators. We have two feed-forward neural networks, which play a min-max game between one another. Sure, fine. The generator, sure, give an overview of GANs. All right. Yeah, I think Breakout. I think you tuned in relatively late, right? So actually, this tutorial actually talks about it a bit. So I made this very convoluted drawing, which I can redo for you real quick. Don't worry about that. I'm happy to explain it again. So we did a lot actually, but the general idea is so powerful and so simple, and that is kind of why I fell in love with GANs. Well, I didn't fall in love with GANs, but like the general, like the concept of a GAN, I think is so cool that it deserves to be repeated. So we have the basic components of a GAN. Can I scroll up a bit more because I'm running out of space here? I'm gonna zoom in again, and maybe another time. No, only once. So the concept of a GAN is the following thing. A GAN consists of two things. Oh my computer is really slowing down. Maybe because the file is too large. So a GAN consists of two things. The first thing is the generative model. Let's call that model G. The second model is called the discriminative model. Let's call that model D. A very nice analogy. So I'm gonna draw. So let's start with. So we can think of an analogy. So the discriminative model can be seen as the police, and the generative model can be seen as the counterfeiters. So not terrorists, but people that make fake currency. So we have the discriminative model. Let's draw that here. And the discriminative model checks whether the currency it sees, whether that's fake or real. So it outputs a probability. So it takes in a bill, and it takes and it says, okay, I can say with this probability that the bill is real. So we have real data. We have like real training data. So real training data, which are in our analogy are real bills, right? So real money. Then on the other hand, we have fake money. We have fake currency. So we kind of have fake training data. And it's the discriminator's job to kind of separate these two and we hope that by training the model, the discriminative model becomes better and better at separating the fake money and the real money. But now the question is, how do we get the fake money? So the fake money is generated by the generating model. So the generative model, often called G, creates the fake money in some way, which we are going to abstract from right now. And of course, so the goal of the generative model is to in every iteration, the generative model tries to get closer and closer to the real data. So in every training iteration, the fake currency they're going to make is going to be better and better, and it's going to be better and better at fooling the police or fooling the discriminative model. But of course, at the same time, the discriminative model doesn't just stand still. The discriminative model is also going to get better and better at separating the fake currency from the real currency. So having these two models fight against each other is what I think is the core concept of a GAN. And I think it like a GAN specifically talks about networks, right? That's the N for Generative Adversarial Networks. But I think that the GA part is way more important. That the GA part is the real key here, because who says that this needs to be a neural network, right? It doesn't necessarily have to be a neural network at all. Like it could be any other machine learning model that is able to generate data and classify data. So was that a bit clear? Breakout? All right, I hope I was able to get you up to speed. So that is what I think, at least, is the core concept behind the GAN. Like, it's nothing more, it's nothing less, but the key concept is that you put two machine learning algorithms and you make them fight against each other, making them better and better. And as the evidence in recent years has shown, right, we can generate crazy images. We can generate crazy lifelike images. So what you're saying is, if I can apply some other supervised, like a random forest, to be a discriminator, yeah, definitely. I think that is definitely I think it's not limited to neural networks at all. Yeah, so neural networks have some nice properties, right? So neural networks have the universal approximation property. In the original paper, they also talk about using max out layers. But recent evidence, or just in general evidence, has shown that GANs need a lot of fine tuning. So there's definitely room for improvements, and who says that? You know what? Maybe might be interesting is can we chain them together? Maybe. I have no idea what I'm saying, but would it be possible to make a GAN chain? Because I'm just thinking about puzzles, right? So imagine this is a puzzle or something. I have no idea what I'm saying. I'm just throwing some stupid idea out here right now. Maybe it's not stupid. It probably is, but so maybe if we can see this as a puzzle, this is probably going to sound very stupid, but maybe can we see this as a puzzle piece, right? And then after this, we can use this model again to because this is a neural network, right? So we can just we can use this to, if we feed in noise here, we can generate new data. So, and this can be used as a generator. This can be used exactly as this, and we kind of get but this idea is probably very stupid, so don't take it too seriously. But hey, I mean, this is how new ideas are born, right? And then again, you can get, so this is your new discriminator, and then you can again try something like this. Just forget about it. But I just thought I'm just going a bit crazy here. Okay, so we're getting sidetracked here. So the general idea of a GAN is clear. This is the original paper, but we're interested in the tutorial because the original paper is extremely light on details. All I'm looking for is a description of how many layers I need, what activation layers I need, how many hidden layers I need. That's the only thing I'm interested in, but the internet is being really unhelpful today in helping me in this. Because, I mean, everyone is talking about this loss function, which is clear, but all I want is to know how much layers to use. Okay, blah, 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 alternating, blah, 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 blah. If you're interested, you can read the original paper, blah, blah, blah. We did that. As mentioned in the introduction, the most popular use is using convolutional neural networks. Okay, Jesus Christ. So we take 64 times 64 times RGB. Then the generator takes, okay, so the generator takes a vector Z, noise, and produces an image. So that is exactly that. So if can I remove this? I can quickly erase my silly idea here. I can erase my silly idea. So if we get rid of this, if you have any questions during my explanation, feel free to post a question in the chat. I'll get back to you as soon as I can, as soon as I see it. Any popular use of GANs that is not images? I have no idea, sorry. I haven't, yeah, images, I think I read in the other tutorial, short videos, right? I think you said short videos. I think it's up here, short videos and something else. Short videos and robot behavior. So robot behavior is another one. What other applications can you think of, Breakout? Sorry, I just called you Breakbutt. Okay, so we read the original paper and it was useful, but not as useful as we ultimately would have liked. So this is kind of stuff that I need, right? So we take noise and we make a fake image. The discriminator takes both the real images and the generated images and produces a probability px for them. Once the network is trained, we would like to generate new images from it. Sure. This kind of network is called a DC-GAN. This is a deep convolutional generative adversarial network. It all has very cool names. So it kind of upsamples and it downsamples. All these architectures look insanely cool, but I mean, I'm kind of in a philosophical bind about these kind of models, right? Because I'm classically trained in econometrics. So I have this background in applied math with a sniff of economics. I'm not a fan of economics, but I mean, it's grown on me, I guess. I wouldn't call myself an economist. I way prefer either a machine learning engineer, software engineer, or data scientist. But I think data scientist would be the best fit. But my problem with these kind of machine learning models is that, I mean, of course you have a publication bias, right? So you try 100 different models and then one of them will probably work. But why? It's just data mining. It's not data mining, but at some point I get whiffs of data mining. Because what is the theoretical justification for using such a large model, right? So if you're looking for trading strategies, if you're looking for patterns in stock prices, of course you're gonna find one. If you look at a million stock prices, you can if you look at a million trading a million algorithms to trade stocks, you can always rank them in terms of performance. So there's always gonna be one that works the best, right? And whether that's due to something theoretical or whether that's due to some anomaly in the data, there are philosophical differences that yeah, that I'm not entirely sure of what my position here is, because like what other thing would we have, right, than to just try different models. And I think I read some posts on Hacker News or Reddit or about Google having like auto ML, like automated machine learning, like picking the model automatically, right? Because in economics you have these kind of information criteria. I think it's not limited to like econometrics, but you have like the Bayesian information criteria, you have the Ikaike information criteria, and there you look at the log likelihood in comparison to the amount of parameters where you like where you penalize the log likelihood by the amount of parameters or some function of the log likelihood and the parameters. Then of course, who says that that measure is a good measure of model fit? So we can continue talking about this in circles for ages. So let's continue. In the tutorial, I train it on the MNIST dataset. We are only on black and white. Our generator produces 32 times 32. Why 32? I have 28. With this, show everything you need to train your own GAN extension, changing the G to D. Okay. Okay. We have input data. Okay. We have a leaky ReLU. Many economists are getting into machine learning. Have you heard of Susan Athey? She has a very nice paper on the application of machine learning in economics. Yeah, she's from Stanford, right? Yeah. So when I was younger, I was very. I think I sent her an email once. I don't think I heard anything back from her. I think she got her PhD from Princeton when she was like 23 or something. I think she's like a super genius. Um, I think her husband is Guido Imbens, who is Dutch actually. And I'm also Dutch, by the way. And he gave a talk in Rotterdam, which I attended. Admittedly, it was not as interesting as I hoped, as it was about causal inference. But I'm starting to kind of, I don't want to say lean more towards causal inference, but I think that a very important thing is that, I mean, of course, like when is something correlation and when is something causation, right? And having a theoretical justification that you can actually say, okay, I did this and now I know for certain that it was caused by this, right? And how they do it is like with treatment effects and all other kind of A/B testing. But I don't know, I've always been very aversive to kind of treatment effects. I don't know why. Maybe I should take another look at it. But when I had it in school, so I majored in econometrics. Well, in the Netherlands, you have like a special degree which is just pure econometrics. It's basically just math. It's just applied math. It's very rigorous. It's very mathematical. I also took PhD math courses in asymptotic statistics and measure theory. And I wish I took measure theoretical foundations for machine learning, but it overlapped with one of my courses, so I couldn't. That was a shame. But yeah, so my math background is big, but admittedly, it's not as rigorous as a pure math background. But my math basis is very strong. But yeah, causal inference. I think a guy named is a bit of an understatement. I think Judea Pearl also has like written books about this, and I think that thank you for giving me another idea of what to do here, because I've been thinking of maybe like just reading a book on live stream and then like going through it like sentence by sentence, right? Because I think there are like a lot of interesting books that I have to read. I don't have to read, but like Judea Pearl, causality, right? No, it's just nice that I'm getting like new ideas for new kind of live streams. So I've been thinking of so there's this very good book called Machine Learning by Bishop, I think, which is basically kind of, I don't want to say the gold standard, but it's a very good introductory book about pattern recognition. It has a good mix of like intuition and math. And I was thinking of maybe like doing a read along with this and just going over each equation with you guys for those that are interested in. I think I will only get like maybe 1 or 2 viewers. Maybe try to program in all the stuff he's doing in Python. Um, because this book is I know it's a good book. I don't have it, but a friend of mine had it, and if I needed to look something up, it was usually in there. So okay, I got a bit sidetracked here. I have to write that down, sadly. Yes, I got sidetracked. I talked about Judea Pearl, Susan Athlete, Judea Pearl, talked about pattern recognition. I got new ideas for a live stream though. That's very cool. So our goal was to train. I mean, we haven't really gotten anywhere with this so far. Like, what time is it? We still have 10 minutes in this cycle. So in all honesty, we haven't gotten anywhere with training yet, and I'm feeling a bit tired. All I want, okay, I think at this point I'm just going to say, screw this, and just gonna take a single hidden layer neural network without any max out, just with sigmoid activations. Because I mean, we have to do something, right? Go back to GANs. Yeah, no, it's fine. Like, I don't mind being sidetracked at all. I think it's nice to interact with you guys. Because I mean, of course I'm in this for me, but I'm also in this for you guys. Yeah, I'm gonna save this and then I'm gonna shut it down because it takes, I think, a lot of memory. Let's go. No, actually, like streaming on Twitch, my focus has been off the charts. Look, we've done 3 streams already, and in this stream, I like, if it allows me to open, I focused for like. This was my very first stream, which was awesome. We made a neural network. Then in the second stream, we started using GANs, right? We started thinking about GANs, and then in this stream of today, we're still working on GANs. I thought that we could fix or finalize the GANs in this session, but I'm afraid that we'll have to put the coding tomorrow or this weekend or maybe Sunday, because I'm very busy tomorrow and I'm very busy this Saturday as well. So maybe I'll be on Sunday again. If I actually am gonna stream, I'm gonna make a countdown for you guys. I will implement a countdown timer. So we want to train the discriminator. Okay, so that's our only goal right now, to train the discriminator. Okay. So let's think about how we're going to do that. We can get rid of this, can get rid of this, can get rid of this. So I'm finally glad to open some code again. What should be open here? Probably Stack Overflow. So this is the neural network.python. This worked. We made this in the first session. Then we cleaned it up. Feed forward, it does the prediction, right? So feed forward does the prediction. Then we have the back propagation, which updates the weights. Which updates the weights. So calculate the derivatives, and then we update the weights. This is not true anymore. This is not true when we're going to change the input and output. We can choose the amount of hidden layers, and we are going to use sigmoid. Maybe we can use a leaky. Maybe we can use a leaky relu. So let's see, where do we have sigmoid? Sigmoid here. I think using a leaky rectified linear unit is way faster, right? But you have to kind of pick that parameter by yourself. And with the sigmoid function, I don't think you need to pick a parameter at all. Of course, you can put a parameter here, which you can choose using which you can choose as a hyperparameter, right? Okay, so we have this. Then what we are going to do, we are going to, all these statements are not true anymore because we're going to change the amount of hidden layers. Okay, so we can get rid of this data actually. Now let's keep it for 1 second. Because we kind of okay, so this is the main file of our GAN, right? This is the main file of our GAN. So what are the ingredients that we need? We need the training data. We need the fake data. And how are we going to get the fake data? The fake data is generated by the generator. For the time being, we can just make the fake data, make it real data, right? So we kind of we can just leave the generator for what it is at the moment, and we're just gonna say, okay, the generator is fake data, and then we have, what other elements do we have? We have the training data, we have the fake data, we have the generator, we have the discriminator. So these are the most important things. So here we are loading in the training data. Then we normalize them. Then we one-hot encode them. Then we set the random seed to 2. And then we change them in a train test validation split. And we generate the random input. Okay, so sorry for the silence. I should be thinking out loud. So I'm having two kind of, I don't want to say conflicting ideas, but there are two ideas in my head right now, because we need to, so what we need to do is we need to specify a prior for the noise, right? We are gonna specify the PZ of Z, which is the prior of the noise. For example, that's my timer. For example, we could choose PZ, Z is normal, with some mean and some variance, right? But I think what we could use is we could specify PZZ to be uniform between 0 and 9 inclusive. So we just generate the label, etc., right? So we generate a uniform distribution of labels. Because and then what we do, we have a neural network that takes in these features. It takes in one hot encoding of it takes in 10 features. So it takes in so for the generator specification, which is going to generate fake data, right? So the input is going to be a 10 times 1 vector of one hot encoded numbers between 0 and 9. So that's 10, right? So it's gonna take in like a vector, for example, that looks like 1 and then all zeros 10 times, 9 times after that. What the output is a 28 times 28 times 1 array of numbers. It's a 28 with elements between 0 and 1, which is continuous. So it's actually like a grayscale value between 0 and 255. But because we normalize the data such that everything is between 0 and 1, we want the output to be 1 as well. And then for the generator, in the middle, I mean, we have input, we have output, and something happens in the middle. We have a hidden layer of, I don't know, like, let's say, hidden layer nodes, or hidden nodes G, amount of hidden nodes. So that's a number to do, right? That is a number to choose. So I think we already calculated the amount of parameters this gives, because we have we have a 28 times 28, so that's 784. I calculated this yesterday. We have in total, trust me on this one, the amount of parameters here are 784 plus 10 for the one hot encoding times the amount of parameters, and what we are assuming here is that the biases are 0. This is definitely a very strong assumption, and it's going to mess with our model very hard. But we built our home-brewn neural network in our first stream without biases, because we followed a very bad tutorial which didn't include any biases. So we are kind of stuck with that now. I'm gonna keep that and just see if it works, right? So the first thing we want to do is get something working, something simple. And then if that works, we can try using like standard libraries, like, I don't know, TensorFlow or Keras or whatever other library there is. Maybe NumPy or SciPyLearn or scikit-learn, right? Okay, so that is the generator. That is a general idea for the generator. Are there any questions about the generator? I'm quickly gonna, I don't want to take a break because I'm kind of into it, but I am going to note down what we did here. I am going to write down what we did in our superwork file. Ending time is 3:30. Actually, I keep working more than 45 minutes, but it's fine. It's, of course, it's not 3:30, but it's 15:30. Did we complete the cycle? No, we did not. We did not finish our work, because the goal was to train the discriminator, which we haven't done, so technically we failed. What we did, we talked about a lot of stuff, and then we started coding again. So we started coding again, and we are getting an overview of how to change the code such that we can train our GAN. Finally, can finally start training our GAN. I'm not saying that it's going to be good. I'm pretty sure it's going to be bad, because I've been warned by people that GANs need a lot of fine-tuning to work. But yeah, I mean, let's keep trucking. Things to improve next cycle. I'm open for suggestions. Suggestions for improving the next cycle. What do you guys want to see more of? Please let me know in the chat. I'll be checking it regularly. So yeah, please come up with a suggestion. 3 times in a row I forgot. No, 2 times in a row I forgot that I had my Be Right Back screen on. It's 30 to 4. Can I do another session? Yeah, I can do another. Okay, so this is gonna be the last session. And I just started the timer. I should actually take a break, but I'm going to not to. So, let's see what we got here. So, any questions about the generator? If not, I'm going to continue. Otherwise, you can always post them in the chat if you have any other questions left over, right? So, we're just going to go with the most simple model we have for the generator. It's not going to be good. It's not going to be pretty. And I might actually have to, because I have to change this code, right? Because the input and the output is, can I go to the neural network file? No alternate file, sure. Let's go to the neural network. Okay, so we have the amount of hidden nodes is k, we can choose that. The input is x, which is going to be 10 times 10 for us right now. It's going to be 10 times 10, 10 times 1. The hidden layer is going to be k. And then the y, the self y. So y is y, okay, is np zeros of the shape. So the output is going to be, okay, so this is fine. So there's no real hard-coded dimensions anywhere. So this is quite flexible. So we take a full, like, there's no learning in these parameters at all, but okay. And then let me just make really sure that we have no hard-coded things anywhere. Nope, we don't. So that's good. We might have to reshape. We might have to. Okay, I think we're forced to reshape the y into a. We're forced to reshape the y to a single 784 times 1 vector, and then shape it back, right? Because that's the output of our model. So that's for the output. The input is a 10 times 1 vector. And then what are the parameters? Are all the hidden weights, right? Are all the weights of the elements of the weight matrix. The biases are, so that's the generator. So this is the where I have to choose k, right? I have to choose k. For the, okay, so we specified the prior, which was uniform. We specified the generator, which we're going to take as a single hidden layer neural network. Then for the discriminator, the input is going to be a 784 times 1 vector of values between 0, 1. Because these are all going to be like, so the input of our discriminator is going to be just a vector of features, like it's going to be the pixels, right? It's going to be the grayscale values of the pixel, which you probably have to reshape or rescale. Maybe we can just work with the vectors and stack them into a matrix, but we'll see about that. Because right now we have them in 28 times 28 arrays, I think. Okay, then what is the output of the discriminator? The output is a single number, p real. So it's the probability of the image being real. That's it. The probability of the image being real is just a number, and I don't have to specify anything for this, right? I don't have to specify at all where I don't specify anything about this. Okay, so I'm a bit stuck here with the updating of the weights because I don't think what I'm doing here is correct. I don't think what I'm doing here is correct. I think this is wrong. I think this is wrong because why is this wrong? Why is this wrong? Because the loss function we're doing is not anymore just the standard squared loss, right? This backpropagation only works so we update the weights, right? We update the weights sorry for having to think so hard, guys. Because I think we need this expression. I think we need this expression, right? Yeah, I think we need to backprop with this thing by sending it stochastic gradient descent, but I haven't done stochastic gradient descent yet. I mean, it's just stochastic gradient descent. I know what gradient descent is, and I know what something stochastic is, but I haven't put like one and two together. So we need to update the discriminator rates by ascending its stochastic mini-batched gradient descent. But how do we find that? We need the derivative of this. How do you get the derivative of this? Like, you need the derivative with respect to the theta d of this whole big gnarly thing, where d is some weird neural network, and because when we built the neural network, we were able to write out the backpropagation explicitly because we use the squared error loss, right? We use the squared error loss, and this so this is the loss that we are having. So this is our loss function, right? So can anyone confirm? This is the loss function we're using for D, and this is the loss function we're using for G. Could someone tell me I'm correct here? Or tell me I'm wrong? Like, either one. I'm happy with both answers. So, loss function log dx plus just me bro underscore says second is the gradient function for G. Yes, it's the gradient function, right? Yeah, so what we want to do is we just want to update, right? We want to update the weights of the neural network. Oh, sorry, I put it to the other screen. So, what is this? What's this screen? Photoshop, huh? So we want to update the weight. So this is basically this step, right? So apply descending, it's a nice like descending. It's I can't type it anymore. Descending its stochastic gradient. This is not the stochastic gradient, by the way. And this is exactly the, like, these we have to calculate, right? Oh man, so so they are both neural networks, so it should definitely be possible to explicitly write out the derivatives in the case that, like, theoretically we should be able to write out the differential with respect to the theta, right? Because there are two neural networks and you're just chaining your neural networks together, but I don't think I want to do that. I don't think I'm ready for that at this moment in time, right? So maybe using our own neural network is not, like, we understand the concept. I just think it's a shame that I can't program it in myself right now, because unless someone knows, like, a Pythonic way of kind of numerically approximating the thing, right? Thank you so much, Espartaco, or SP4TR4CO, Espartaco. Thank you so much for following. Really appreciate it. Yeah, welcome, man. Thank you so much for joining us today. We're almost done, actually, but you followed me, so I think you'll get a. Can I? What is this button? Can I replay it? Or because I missed the sound. Oh, oops! I clicked on something. I don't know what it is. Hide or something. I'm not sure. Okay. Thank you so much for following. Man, this is tough, right? Because I'm really certain you can take the derivative of this, because we did that here. But wait. Here, this is the derivative of a single neural network. Where the loss function was okay, so let's see if we can just, for the time being, because I'm not sure how far I'm gonna get. So let's just start and see where we end up. Well, like, maybe it turns out not to be that difficult. I'm scared it will be, but you know, who knows? Maybe it will turn out to be fine. So I think that the trick here is to take it one step at a time, and like and to, like, not get overzealous in the sense that all right. Okay, so I mean, we got to start somewhere, because we want to find an analytical expression for this beast. Okay, so we're gonna assume m is 1. No, we're gonna not assume m is 1. Assume m is 2. I mean, do we even want to use mini-batching? So can we do it without mini-batching? I'm pretty sure we should be able to do it without mini-batching, right? So instead of mini-batching, you just take all the, you like take your mini-batch to be, you take your mini-batch to be as large as your whole thing. Okay, so you guys probably are having a blast seeing me struggle here so badly. Okay, so what I want to do here is take the derivative of the log dxi with respect to the delta theta d, right? So if we get rid of, if we just I think because taking derivatives is a linear operation, we just have to think about what it looks like for the ith element, and then we can just plug in I is 1 to m, right? So we are going to take a look at the derivative of log d xi. Oh man, this is going to be tough. Whew, with respect to delta d. In this case, I think D is just your standard neural network. So we have input 1, input 2, input 784. This is your first hidden layer. No, excuse me. This is your input layer. Then for the hidden layer, we have 1, 2, up until K, D hidden nodes in the first hidden layer. And the final output of the neural network is a single number, right? It's a single number. And all these are connected, right? These are connected. These are connected. These are connected. So, yeah, I'm sorry for this terrible, terrible exercise. But I think if we go back to the first stream, or to the results of the first stream, I remember that in that tutorial, so we followed this tutorial in the first stream, where we built the toy neural network, right? And what happened was that I found some, look, we need this. This is exactly what we need. We need this formula. We need this formula here. Why? Because let's say the P real hat, right? So the probability hat is just the sigma function of W2 times sigma function of W1 inputs. Because we set the biases to be 0. We set the biases for all of them to be 0. This is a very strong assumption, and it's not correct at all, but because we're writing our own stuff, we're gonna have to make concessions somewhere, and I think that putting them in the biases is kind of okay. So in that case, the loss function was actually like a squared error loss, right? So it was a summation. It was a squared error loss, and in our case, so that was a squared error loss, or rather FY hat. Hey, Silence! Oh man, you came. I don't want to say you're late, but this is like the last session we're gonna do. But I'm very glad to have you here, man. Yeah, so enjoy the last leg, where we are trying to, I think, attempt the most difficult thing we can do here, and derive the analytical expression for the derivative of the loss function for a standard multi-layer perceptron GAN, because holy mother of things, I want to do this myself. So I want to program this in myself, but we need to do this with, we need to make like a stochastic gradient descent, but at the same time, like the neural network we programmed in only had backpropagation, so it's not going to, and the backpropagation we programmed in here is like, this works because the loss function, we took that, so this works because we took the log. This works because we took the log loss function as, what is it, y minus y squared, like y minus y prediction squared, right? Silence is asking, how is the learning process going? You seem to be understanding most of what you are reading for the neural network. Yeah, so understanding and programming in the neural network went fine. So the GANs turn out to be significantly more difficult. I think the idea is very clear, but I'm currently lacking a bit in execution, because so what I'm lacking here is like, I don't want to use standard libraries to do this, but I'm afraid I'll have to revert to them in the end, because we have to like, we have to finish the project some way, right? I really like how we got the general idea working, and we actually went through the whole original paper. I think you missed that as well. We actually together we read the whole original paper on GANs, and we came to the conclusion that actually the most important information is not in there. I mean, there is a nice analogy here, which says that you have the people that are making fake money, and then you have the kind of the TSA or the police that is trying to separate fake money from real money. So there are some nice analogies there. But it says here, like, in this case, I think this is a key part here. So in this case, we can train both models using only the highly successful backpropagation and the dropout algorithms. So, like, I'm trying to get that dropout, like, there's no appendix or something, right? There's no, okay, you have a fully connected neural network, here are the formulas for the backpropagation. So maybe I should Google that, right? Maybe I should Google GAN backpropagation. That's maybe that works. Only NumPy. This seems like a guy who's using only NumPy and he's implementing GANs. Unrolled GANs. GANs. Is this already deep learning? Can anyone explain to me, like, am I using deep learning already? Or is it just machine learning? Like, I thought that the deep learning just refers to like having a huge amount of hidden layers, but I'm not sure, like, is it deep learning already? Or is it just standard machine learning? Wow, this is cool. Like he implemented a GAN. Like, oh, am I doing deep learning? Oh, that's awesome. Wow. So yeah, shit, you're being sarcastic. I might need your help understanding the linear algebra to get an understanding of the topic because I failed that test. Did you? But you got an 83 on that test, right? Or wasn't 83 not enough? No, thank you. I don't want to join. Please, just let me read. Okay, I've been streaming for 3 hours and 14 minutes. Actually, I've been streaming for 5 hours and almost 50 minutes because I changed the quality of the stream and now it's way better. It was the test after the one on Tuesday. Oh shit, yeah, of course. You can send a message in the chat. Maybe I can help you out. Maybe I won't know the answer either, right? Or maybe someone else in the chat will. Otherwise, I always found Reddit to be a great help. I passed that one but failed the one before. All right, so what is the concept you're struggling with? Look at this stuff. This is amazing. This is really amazing. He did it with only NumPy. That is really cool. And Atom Optimizer. I don't know if that's cheating, but that's really cool. So what is this? I think I need these. Right? So we have the yes, I think this is it. Guys. I think this is exactly what I've been looking for. I don't want to be too happy yet, but I think this is exactly what I need. I think these are exactly the equations that I'm looking for, except for the fact that he's using a rectified linear unit as the first layer, and I don't know what a G is. I think it's a sigma, right? I think that's a sigmoid. I think this is a sigmoid here. It must be, I guess. Layer 2 activation. I think this is either a G or a sigmoid. But I think this is what we're looking for. So I'm gonna stand up a bit. Oh, because my back is killing now. So it's not killing me, but I mean, sitting down too long cannot be this healthy for your back, right? So it's gonna stretch out a bit. Because I think we have it. I think this is the treasure that we've been looking for. This is what is going to allow us to estimate the model. And why? It's so crazy, right? If you would have shown me this image 3 days ago, I would have no idea what I was looking at. But now together, we've done so much machine learning that I think in all honesty, it's so amazing that like what we've done together, right? Maybe can you guys see me like this? I'm just gonna look at myself and I'm gonna see whether you guys can see me or not. Because looking at my chest is not that interesting, but maybe. Yeah, you guys can see me like this. So I'm sitting on the floor right now. I think it's sometimes better than sitting on a chair. Anyway, so what we're looking at here is, wait, how many minutes do I have left? I have 15 minutes left. I think I'm going to cut this session short a bit. Not now, but in like 10 or 5 minutes. So, what we see here is we see a 2-layer neural network and a 2-layer discriminator. Wait, is it true actually? No, where is the discriminator? So this is the discriminator. In the first layer, we have the data times the weights plus the biases, right? I'm going to open this in Photoshop and I'm going to draw all over this bad boy, because this bad boy is what is going to give us the ability to program this model in. This is exactly what we need here. So what I'm seeing here is we have I think a 2-layer. This is like the simplest model we can have here. We have the discriminator looks as follows. We have an input layer. We have one hidden layer. And we have a single output layer. And my current interpretation of these things is that, so in our case, we have no biases, so screw that. And we have no biases here as well, screw that. So the weights here, so the numbers that we plug into the activation function, into the layer 1 activation function, so L1, is just data times weights. Then the activation function that is being used here is a ReLU, so a rectified linear unit. So we got these two, right? We understand these two. Then for the second layer, we also the numbers that come out of here. So the numbers that get out here, these are exactly these numbers. And then the final output is going to be the sigmoid over that thing. This is going to provide us a number between 0 and 1, which is exactly the probability of the image being real, right? So that's the discriminator. That gives us the discriminator. But more importantly, it gives us the formulas for updating both of them. Yeah, sure. And then here we have minus log L2A plus log 1 minus L2A. I'm not sure whether this is a typo, because I think in the original paper, let's look at the cost functions here. So this is for the this is for the discriminator, right? So for the discriminator, we have, that's the first part, the discriminator. We have the log of this, and then 1 minus the log of that, where these are the fake data. So I'm not sure why there's a minus here. I'm pretty convinced there should not be a minus here. I'm pretty convinced it should be a plus. But if someone else is willing to check this with me, because I swear to, like, the cost, right? I mean, so this is the probability of a real image. So log is a monotone function. So if the probability of a real goes up, that means that the discriminator is doing better. So that means that the log of this is going up, and that means that the cost is going down. Well, that kind of makes sense. That does make a lot of sense. But then why is it not the case here? So if the probability of getting a good image goes up, then the log of this goes up, and then the cost goes up. Why is there no minus here then? So this is the probability. So this is the part where we try to classify the real images, right? So this is the part where we try to classify the real images. If we classify the real images better, right? If we classify the real images better, so D goes up, then log D also goes up. Then the cost goes up. I don't get this. And then for this part, if we are making the generator better, then D goes up, which means that this goes down to 0. This is frustrating. I think I'm gonna call it quits pretty soon. I mean, people are leaving, which I can totally imagine, because this is not the most interesting thing to look at. But it is part of machine learning, right? Like kind of powering through the difficult equations is it's not always just banging on your keyboard coding 24 hours a day. While that would be, of course, really awesome, but it's not always the reality that we're living in. So I'm just gonna assume for the time being that these equations are right, and I will in the next session I will try to change his change functions and I will make them use both a sigmoid, because we don't use a ReLU, we use a sigmoid here. And for the, I don't see the generator anywhere, but I think that the feed forward is just predicting using the same network. I think we can use the same network for both of them. So yeah, you're taking the derivative of the log function. So this is what I tried to do. This is what I tried to do, but kind of failed here. And so what did we learn? We learned that you need to Google. You need to Google stuff before you try to do it yourself. So what I've learned: learn how to Google equations before you try to derive them yourselves. We deeply learned how GANs work, and we actually read the whole original paper quite critically. And we figured out that the paper is extremely light on very crucial details, but of course the paper is very important. So I just think I'm gonna debrief myself here. I'm gonna finish this cycle. I don't think I want to note down an ending time because I haven't worked for. Okay, I have 5 minutes. I think that's fair. So let's say 7:4:10 or 16:10. I didn't set a goal, but kind of wanted to wrap it up, right? I think I did that. How will I get started? Any hazards? No. Okay, did we wrap it up? Yep. We kind of, okay, a big thing. We found the correct equations for the single hidden layer NLP, artificial neural network, to make a GAN. Any distractions? No, not really. Things to improve next cycle. You guys tell me. What do you want to see? What did you like? What did you dislike? I'd love to hear some feedback from you guys. All right. So, what did I get done this day? let me see. So what did we do? In the first cycle, we watched Siraj. Then we started reading the original paper. We got all the symbols straight. Then we fixed the stream and we got a bit of the value function. We finalized the calculations and the derivations. Then we started coding and thinking about like, what are we going to do? And then in the end, we Googled and we found some correct solutions. So we started off by watching Siraj's video, which was useless. No, it was not useless. It was like a bit useless. And then we started reading the original GAN paper together. We finished the whole GAN paper while fixing my stream in the process. It has much higher quality now. Then we started coding, but we ran into the problem of our backpropagation being hard-coded for the squared error loss function. Then we Googled, we first tried to derive this manually, but we ended up Googling the equations and thankfully found them. How did this compare to my normal? Kind of good. I mean, again, like so GANs are like GANs are a tough cookie to crack. Like, wait, I should put it in the next one. So here, GANs are a tough cookie to crack. See, like this is exactly what machine learning is about. Like you hear everyone talking about GANs, but then the moment you try to program one in, the moment you really try to understand this just the simplest of GANs, you suddenly get stuck in places you couldn't imagine, right? So this is why I think it's so instructive to do this together, because you might think you know how a GAN works, but if someone asks you, hey, could you help me with this GAN? You're like, ooh, I don't know, sorry, right? Besides that, I think it was a lot of fun. You guys saw me struggle a lot. You guys helped me a lot with fixing my stream. What went well? What went well? We went over the original paper, dissecting all the symbols one by one. I think this is very instructive for me personally, and I hope for you guys as well. I tried to explain the general concept of a GAN as much as I could, and hopefully I educated someone a bit on what a GAN is and can do. Any other notes? BRB screen, but that was a bit funny. Maybe a standing disk. More coding. I want to see more coding. Like, I want to see more coding for myself, mainly. How does this compare to my normal? I mean, good. Very good. We weren't particularly effective in the sense of having written lines of code, but we did do a lot of theory, etc. Whew! So that's that. Let's save that up. Wow. Wow, that is another stream. Yeah, so again, I kind of wish we we would have been finished with the GANs by now. I don't want to say I'm getting sick of the GANs, but I was secretly hoping we would make more progress today, right? But you cannot. I mean, if something turns out to be more difficult than you anticipated, you cannot really do anything about that. I hope I was able to provide an entertaining but also educational stream on GANs, and next time we will really try to get into that programming because we finally found the correct equations. During the last two cycles, I noticed myself already getting tired a bit, like mentally, because we had to think so hard and we had to read the original GAN paper. In the end, we spent, I think, 3.5 hours, well, like 3 times 45 minutes. So let's say 4 times 45 minutes into really deeply reading the GAN paper. So it took us 4 hours out of the 6. It took us 4 blocks out of the 6 to like really get into the nitty gritty details of the GAN paper, and then in the end it even turned out that there are no equations. There. So yeah. So I think the stream has been successful. We had some familiar faces pop up. We got 2 new followers, Breakout and Espartaco. So I'm very happy that you guys were willing to join with me today. I'm not sure if I'm streaming tomorrow. I'll try to get a stream countdown up ASAP. Yeah, so thank you so much for having me. I've been streaming for like 6 hours straight now, so I'm gonna take a break. If you have any more questions, you can always put them in the comments or email me, message me, DM me on Discord, whatever. DM me on Twitch. Post it in the chat. I'll try to respond as soon as I can. If you have any suggestions for future streams, whatever, just let me know. And yeah, I hope I was able to provide some educational and entertaining content for you guys today. And I hope you learned a thing or two. So I'm going to go now. Thank you so much for joining me. Thank you, new subscribers. Thank you, everyone who watched. I really appreciated you having you all here today. So yeah, thank you so much. I'll see you guys next time. Is it learned or learned? I'm feeling so dumb right now. Is it, we learned? We learned a lot. We learned or learned. It's like basic English. I think you guys can see that I'm relatively tired. Both are acceptable, okay. Learned is more British. Okay, sure, whatever. Alright. I'm going to stop the stream now. Thanks, guys. I really enjoyed having you all. And hopefully you guys are going to tune in next time as well.